This video describes the thermal analysis of a steel beam subjected to fire on three sides with the finite element software GmSAFIR. This slide shows the results that we will get at the end of the analysis. You see here a W-shaped steel cross-section protected with a sprayed fire-resistive material and heated on three sides due to fire exposure. The beam section has been discretized with triangular shaped finite elements, and the results are plotted here after 2 hours, showing the temperature distribution inside the cross-section with the asymmetric thermal boundary conditions. The beam is a W12 by 120, and to build the geometry and the input file for this problem, we are going to use the preprocessor GmSAFIR. We will start by describing the geometry for the upper right corner, then we will use Symmetry to create the whole cross-section. I am now going to switch to GmSAFIR in order to build the model. In GmSAFIR, start by creating a new project, File, New, locating the folder in which you want to save your project, and then typing the name of the project, in this case, thermal steel. Click Save, use .geo extension, and open Cascade. We have now created a project in GmSAFIR. In the selected folder, a file thermalsteel.geo was created. To build the model in GmSAFIR, we will follow a 3-step procedure. First, create the geometry. Second, assign the SAFIR-specific properties. And third, build the mesh in order to get the discretization of the section. After this 3-step procedure, we will use the command create.in file here at the bottom in order to generate the ASCII input file read by SAFIR. This file will be located in the same folder as the .geo file where we saved the project. We start with the creation of the geometry. We will create 1/4 of the section and use Symmetry. We navigate to Geometry, Elementary Entities, Add Points in order to create points for the cross-section. We will start typing the coordinates of the points in meter and clicking Add after each point. The first point is 0.00900. Second point 0.009, 0.1228, 0. And we keep going. Fourth point is 0.024, 0.1378. Next, fifth point is going to be x of 0.156, moving on the flange now, adding the thickness of the flange, and the seventh point back to 0.0 for x and 0.166 for the y. We can close now this box. Next, select Tools, Options, Geometry, Point Labels. Now we want to create the points used to define the sprayed fire-resistive material, and we'll do that using the translation command because we know the thickness of the insulation. We select Geometry, Elementary Entities, Transform, Translate, and we'll apply the translation 0.011 in meters, dy0, dz0. We tick the box Apply Translation on Copy, and we select the point 1, And to validate, we type E. You see that a new point was created here, translated by 11 millimeters from the point 1. Next, we will apply a translation of 0.011 minus 0.011, 2.2 and 3. You can select multiple points at once, also 4 and 5. Type E, 4 new nodes are created. We change the translation to 0.011, 0.011. We select 0.6. We validate with E. And finally, 0.0, 0.011 to 0.7. Type E. To quit, we can type Q. These new points will be used to create the SFRM layer on the upper right corner of the steel section. Next, we will create lines. We select Geometry, Elementary Entities, Add Line. We will now define the lines by selecting the starting point and end point of each line. We have to create the lines in such a way that the surface will be on the left side of the line. In other words, we are turning counterclockwise with respect to the surface. So we start by selecting point 1 and then point 2, and you see that the line was created joining points 1, 2. We repeat with point 4 to point 5, point 5 to point 6, point 6 to point 7. Then we press Q to stop this. Now you see that I didn't link point 2 to point 4. This is because here I want to model the root fillet of the steel profile. So I will use a circle. More specifically, a circle arc. I click here on Add Circle Arc. I select point 2, point 3, and then point 4. The root fillet of the steel section has been created. We can type Q to abort. We will now repeat the procedure for line creation and circle arc creation for the sprayed ferroresistive material. So we select line. We go here from point 9 to point 8 to point 9, from point 11 to point 12, from point 12 to point 13, and from 13 to 14. Then type Q. Finally, we repeat with the circle arc, selecting point 9, 10, 11, press Q. Next, we will use Symmetry to create the remainder of the section. We select Geometry, Elementary Entities, Transform. We will now apply a Symmetry. The X directions corresponds to plane A, so we'll type 1 here, 0 for B, C, and D. We will apply Symmetry on copy, and we want to select or apply the Symmetry on the curves. Now we want to select all the curves in the model, so we are going to press Control and left click on one corner, then again press left click on the other side, and you see that I selected all the lines. Then I type E, and this applied Symmetry to get the upper left corner of the section. We now have half of the section. However, the Symmetry action has resulted in duplication of nodes. You can see that by looking at the labels. You see here that you have some labels that are duplicated or that are superposed. To address this, there is a specific command in GmSAFIR to merge duplicated entities. I'm going to go into Modules, Geometry, Elementary Entities, Boolean, Coherence. I click on Coherence, then I will reload the script, and you see that this had the effect that we wanted of deleting the duplicate nodes. For example, here point 4, point 15, we don't have superposed labels anymore. Now we can apply a symmetry about the y-axis, plane B, to create the bottom half of the section. We'll select modules, geometry, elementary entities, transform, symmetry, typing 0, 1, 0, 0, applying symmetry on curves, selecting everything with Control left, and type E, and now we have the bottom half. Again, we will apply the coherence and reload the script to merge the duplicated entities. Finally, for geometry creation, we now have to create surfaces. We have created all our points and curves, but we don't have surfaces yet. We will start by showing the line directions using tool options. And for the normal and tangents, I'm going to increase here the value by clicking and dragging to the right. And this shows the direction of the lines, which will be useful for definition of the surfaces. Because, as I mentioned, we need to have the surface on the left of the lines. To create the surface, we're going to add plane surface. And starting with the steel, we will select one of the lines that is oriented in the right direction. For example, we will select here line 4 for the steel surface. GmSAFIR automatically knows that the other lines should be included in the perimeter of the surface, given the convention with the directionality of the lines, the fact that the surface needs to be on the left-hand side of the line that was selected. Press E to create the surface. We can verify that the surface was indeed created by navigating to Tools, Options, Surface Label, and we see here plane 1 that was created. Next, we create the surface for the insulation material. We'll select here the line 9. Again, GmSAFIR was able to find the entire perimeter, but note that here we also need to select a line that bounds the steel profile because we want to exclude it from this second surface. Here the surface is only the insulation material. That the software GmSAFIR cannot know it automatically. So we need to select an additional line, again with the convention that the surface that is relevant is on the left-hand side. So looking here at the normal pointing to the right, we'll select this line 17 and type E. This created a second plane with its label here. If we want to further check the creation of the two surfaces, we can navigate to Tools, Visibility, and here we have a list of all the entities in the model. If we select only surface 1 and we apply, we see that we have the plane 1 here, which is indeed the steel profile. If we select surface 2 now, this one comes back. This concludes the creation of the geometry. We press Q to abort, and next we will start defining the properties of the model. We start with the general input data of SAFIR. Here in Solver SAFIR, we have a number of model parameters that we can define for this problem. Very important is the problem type. Here we are indeed dealing with a thermal 2D analysis, so we keep this as it is. We can use the time, we can specify the time that we want for the steps at which we print result, as well as the last time step at which results are printed. In this case, we want a simulation to run for 2 hours, that's 7,200 seconds. I also changed the maximum time to 128 seconds, meaning that when SAFIR converges easily in a few iterations, it can increase and double the time steps up to a maximum of 128 seconds. I don't want to allow it to do larger time steps than that. The minimum time steps will be 0.01 second, meaning that if the simulation cannot converge, it will divide the time step by 2 and try again, and divide by 2 and try again. It can do that as long as it does not get lower than 1/100th of a second. If it still cannot converge with these very small time steps, then the simulation will stop. Here you can specify the name of the input file. For this model, we'll call it thermalsteel.in. Another important model parameter is the type of calculation for the thermal analysis. This is linked to the interfacing with the fire model. In this example, we'll use curves because we will specify the fire as a gas temperature time curve. In other applications, we could interface with a localized fire model or a CFD calculation, specifically, for example, with Fire Dynamic Simulator FDS. After these general model parameters, we are now going to define the properties of the materials and boundary conditions. We navigate to geometry, physical groups, and we will add a physical group to the curves to start with. Physical groups are the groups used by GmSAFIR to assign properties to entities such as curves or surfaces. First, we will assign thermal boundary conditions, so this applies to curves. We will start by defining a group which is unexposed for the unexposed boundary conditions. Specifically, this is for the two curves at the top of the profile, which are in contact with the upper compartment, which has air at ambient temperature. So for those two curves, we'll say that they are part of the group, the physical group unexposed. We type E, and next we can specify the properties or the boundary conditions for this group. We'll use a frontier constraint and specify temperature F20. It means that these two lines will be in contact with air that stays at 20 degrees C throughout the fire event. And there can be heat transfer through convection and radiation with this air at ambient temperature. We click Add Update to add this physical group. We can close the window and repeat the procedure, add a physical group for curves, this time typing or creating an exposed group. We'll select the curves of the perimeter except for the two upper lines that were already defined. I selected the lines that form the perimeter of the model, except for the two lines at the top. I can now press E. And for these lines, the type of boundary condition will be again a frontier constraint, but this time these lines will be in contact with the standard ASTM E119 fire. Select Add Update to add the condition, close the window. We can check again what we've done by typing or selecting here View Frontiers, and the model is indeed correct with application of the thermal boundary conditions as desired. Next, we will define physical group properties for surfaces, specifically assigning materials. Select Add in physical group Surface. We'll start with the steel, so typing or labeling it as steel S, and we have to select the plane 1. It is not easy here to select plane 1 because you see that the two planes are superposed. So I'm going to go back to Tools, Visibility, and select the surface 1. This way here I can select plane 1 for the steel surface. Type E. And the plane 1 is now defined as a physical group. We will now define the material associated with this physical group. In property type, we need to define a new type of material because we don't have any defined materials yet in the model. So select new material definition. This material type is metal. Material subcategory, we have several predefined materials. We'll use steel EC3EN for the Eurocode 3 material properties for steel. We don't need to change the thermal properties in this example, and we will define the name of the material as steel M, for example, for material. Select add update. Sometimes we have to click twice, and you see that a new category appeared, material names choice. So now we can pick this defined material. It is now available to be attributed to a physical group. In property type, now select surface material, and now we can use this material steel M to attribute to the physical group for plane 1. Select add update. This material has now been allocated to the physical group that contains surface 1. This can be checked by navigating here to the bottom of the menu and selecting View Materials, and you can see steel M associated with surface 1. We now apply the same procedure to define the material of the SFRM. We start with selecting a physical group surface, defining SFRM S for this physical group, selecting plane 2, type E. We need again to define a new material. This time the type is insulation. We will change a few of those properties. For example, thermal conductivity is set to 0.12 watts per meter Kelvin, specific heat 1200 joule per kilokelvin, density 300 kilo per cubic meter. And in terms of material name, we'll label this material SFRMM. Click Add Update twice. And now in the material names choice, we have two materials defined in our model. We select SFRMM. Now in property type, we can select surface material, use the defined SFRMM and select Add Update to add this material to the physical group of surface 2. Again, we can check what we have done using View Materials, and we see the two materials. You see also the legend at the top with the material type. This is correct. Another useful visualization tool is in Tools, Visibility. In List, the physical groups are shown, including here you see the steel MS and SFRMM. If you select here the physical group and you only want to show the SFRM, you see this surface. If you only want to see the steel, you see this one. This is the physical group for the unexposed lines of the perimeter, and this for the exposed lines. With this, we concluded the definition of the properties. The next step is to define the mesh. There are many options to tailor and specify the mesh in GmSAFIR. These come from the software GmSH, who acts in the background of GmSAFIR for all that deals with mesh definition, and there are lots of tutorials on GmSH. Here I'm going to use a very simple option to specify the mesh, going into Tools, Options, General, Mesh General. We can change the element size factor here and decrease or increase this size factor to have a finer or coarser mesh. Here, let's set it to 0.2. Next, in the module mesh, you see that you can define a mesh 1D, 2D, or 3D. You have to choose the appropriate one for this kind of model. So here we have 2D surfaces that have to be meshed with 2D elements. When you click on 2D, you see that GmSAFIR generates a mesh almost immediately, instantaneously. If you are unsatisfied with the size of the mesh here, it seems a bit coarse, you can click on Refine by splitting, and you see that the mesh gets refined. And you can keep clicking on this option to have very fine mesh. Note that if you are using the demonstration version of SAFIR, there is a limit in the number of nodes and elements that are allowed. So if you use a very fine mesh and the model does not run, make sure to check that in the output file, whether there is an error message specifying that it's because the number of nodes or elements exceeded the limitation of the demonstration version. The model is now completed. You can select Create .in file in order to generate the SAFIR input file with the given parameters. And you see here in the dialog box that this was completed successfully. If we navigate to the folder in which we saved this project, we see a number of files, including now this input file that can be read by SAFIR. If we open the input file, we see all the parameters that are necessary for SAFIR to run this thermal analysis. Toward the end, we have, for example, the boundary conditions that we specified, as well as the materials, in this case, insulation and steel EC3EN. We can now run this file. One way is to double-click on a SAFIR executable copied and pasted in the same folder and typing the name of the file without its extension, then press enter. SAFIR runs, you see all the time steps. The DOS window closes when the simulation is completed. And as a result of this run, 3 output files have been created. A .out ASCII file that can be opened and read here. It contains results in terms of temperatures at the nodes at every time step that is printed. But it's more convenient to look at results to use Diamond. And if you open Diamond and you open this XML file, you can show the solid contour, the properties including the materials, insulation, steel, EC3EN, the mesh, the frontiers, which give you the applied boundary conditions. You see the ASTM E119 fire curve on 3 sides and the F20 condition at the top. And you can plot temperatures which increase over time. And you see here a caption of the temperatures. And you see the progressive heating of this protected steel profile. You can change the options to specify the scale of the temperature, for example, from 100 to 700 degrees with a step of 100 degrees. And now if you scroll here to have the time change, you see this temperature increase in the profile, of course with the 3-sided fire exposure. You can also plot results. For example, here, if I'm interested at the top flange, it's node 186. I can plot a chart of the temperature at node 186. I get here the temperature increase as a function of time. I can add more nodes on this plot. And if I copy and paste this plot in an Excel sheet, I get all the data automatically exported. So this is Diamond, and this shows how to visualize the results of the calculation for this example. This concludes this first tutorial on a 2D thermal analysis of a steel section.